Okay, so today it's going to be 1 hour of me talking, and then we're going to do Q&A with Geordie as well. So if you have questions about any of this stuff, specific, non-specific, that'll be fun. I think this will be really good because one thing, if you're learning a subject, you can have a lot of questions which are more like, how do I orient myself in this world? And that's sort of what the Q&A is for. So like general things which, or just a specific, how you can think of X result. We'll try our best to answer. All right, but so in the first half though, I want to talk about something called Green's correspondence, which if you've seen Alex's recent talk, he talked about in a different context, but morally it's the same, but it's much easier for us. And for that, I want to talk about Krull-Schmidt categories. So this is like a definition which is not on the face of it that strong. It's like, these show up all everywhere. So first definition we're looking at. So C, an additive category. Additive is Krull-Schmidt. I think 10 to the meeting. If, all right, so one, each X is isomorphic to a finite sum xi where xi are indecomposable. So in particular, if we're in an additive category, this is just somewhere where we've got direct sums. So it makes sense to say, an object is indecomposable if you can't write it as a direct sum. Right? And the second condition is that X indecomposable implies that the endomorphisms of X is a local ring. Okay, so I don't think I need any more. Do I need a finiteness condition, or is this it?
If and only, so X is indecomposable if and only if endomorphism is locally.
But isn't that?
I mean, that would be
It's always true.
Yeah.
You don't need to assume that.
Yeah, like if it splits up, the ring won't be local because it's got idempotency. But like I'm wondering if do you need any finiteness conditions to make this work, or was it just local? I mean, anyway, in the context we're working, everything is finite dimensional over a field, but like in general, this is a there's the finiteness conditions on an additive category. And let me say that
so that everyone finds indecomposable means if you write it as A plus B, then one of A and B is 0.
Yeah. So then the theorem, so if C is Krull-Schmidt, then each X in C is isomorphic to the direct sum I equals 1 to the n, xi to the ei, for ei natural numbers, and xi not isomorphic to xj, for n equal to j, and xi indecomposable. Decomposable. And this decomposition is unique in a weak sense. So, and this is, I'll say, unique up to non-canonical isomorphism. Non-canonical isomorphism. Okay, so what this is saying is that any object breaks up into indecomposable pieces, doesn't do so canonically. You can do this to any object. And if you do this, there will be some number of copies of each isomorphism class of indecomposable. And the number of copies is independent of how you broke it up. So it's like saying, you can build things by direct summing indecomposables, and there's a unique factorization property. But it's not saying that the sum is, splits canonically. Okay, and so this follows from these axioms, right? So this is a very general place to live, but this is a really, really powerful finiteness condition on the category. It's like, I think it's, I don't know, like, I definitely didn't appreciate this when I was sort of learning stuff, how useful this condition is And so the rest of like this first lecture will basically be saying, wow, taking direct, like being in a Crucial category is really, really strong. Like for instance, basically all of the results, which I'm going to say, using group app, like we're going to be living in rep G, but you basically don't need to be in rep G, and the proofs almost work as expected. Like it's kind of insane how strong this is, coupled with some group action stuff and the Mackey formula. Yeah, so I just really want to like stress that this is a innocuous seeming definition. Maybe I should say important example, rep KG. So finite dimensional representations of a group, right? And you know, anything finite dimensional can only break up into certain things, and then it's lemmas in linear algebra that tell you that they're endomorphs of groups are local. Okay. Does anybody have any questions about the statement?
Sorry, can you say again why rep G is a local ring?
So this is a general statement about
Fitting's lemma.
Fitting's lemma.
Fitting's lemma.
Yeah. So,
So
yeah.
you have a module and you have an endomorphism. And now you look at the powers of that endomorphism, and you argue that either that endomorphism is nilpotent, or at some point you're projecting onto a submodule which then splits up as a subnet. This is Fitting's lemma, which is very, very powerful basic lemma in linear algebra. Maybe in the questions we can try to recover the proof.
Yeah, so maybe one way to see this, just over an algebraically closed field, say, you have an endomorphism of a vector space. You know, if Jordan decomposition, it breaks up into Jordan blocks with certain eigenvalues in each, right? And then one can check that if you have an eigenvalue which occurs somewhere, like you consider, if you have your endomorphism F, you can consider F minus lambda the identity. So it's worth writing down. So say F goes from B to B, where lambda is a generalized eigenvalue. Then F minus lambda to the identity is also an endomorphism from B to B. And then some power of this basically will be zero if B was assumed indecomposable. Or maybe you could say it can only have one generalized eigenvalue, or its generalized eigenspaces would give a decomposition. And if it only has one generalized eigenvalue, then when you minus this and take it to a high power, you must get zero, because you can imagine it's strictly upper triangle. So in the case of like finite dimensional vector spaces, this is related to like the central stuff I talked about 2 or 3 weeks ago.
Yeah.
Right. Yeah.
And then why does that make it a local ring? Sorry.
Oh yeah. Sorry. So that's much easier. So this says if you're in a ring where every element is either nilpotent or an isomorphism, then the set of nilpotent elements forms an ideal.
Forms the maximal ideal.
The maximal ideal. Yeah. Okay. Fantastic. So now we're going to be really using this along with relative projectivity. So I'll briefly remind you what that means, but I'll remind you with a different definition, and then we can remember what relative projectivity means. Okay, so M indecomposable in rep KG, then its vertex is the minimal, so really this is a conjugacy class, but I'm just going to write it as a single subgroup. So minimal P group Q is the, just to be correct, conjugacy class of minimal P group such that M is relatively Q projective. Okay, so let's remember what this means. This is saying that M occurs as a direct summand of I, Q, G, U for some U. Okay. So the idea is, M, it's going to be relatively Q projective for some P subgroup. You can find a smallest one. You can show that any two smallest ones in the poset of things are conjugate by the Mackey formula. And any element of that unique conjugacy class at the bottom will be the vertex of M. Okay.
Did we ever explain why probably you already did, probably you did this, but why the C log P subgroup always works?
I think I did. So yeah, so I believe that I did, but I'll write down the reason why so we can see. So this is equivalent to M is the summand of I, Q, G, R, G, Q, M, and you always have a map going this way, a surjective map, and when the index of these is co-prime to P, there is a canonical section of it. So that tells you why you there'll always be a group Q which floats.
I mean, I'd say that you always have, like these are bijoint, so you always have a map from M to that and from that to M, and the composition of those is the index of Q and G.
Oh yeah, that's another way.
And so if you take the C log P subgroup, then that index is co-prime to P, so that's an invertible map, so M is a summand inside that. And you're cooking on gas.
Yeah. I don't know if I said what the maps are in both directions, but yeah, I've said that these things are bijoint and you can compose them and check those multiplication methods. And I will also say that this is a general principle which is quite useful. So right, so if you have a maybe I'll just say another instance where this sort of thing shows up. So if you look at group cohomology of a finite group, then you also have these induction and restriction maps. And if it's in characteristic P, you can show that the group cohomology sort of injects into the group cohomology of the normalizer of the maximal of the silent P subgroup. So, and it's by this sort of you bring it down, you bring it back, it multiplies by the index kind of thing. But if your index is co-prime to P, that tells you that certain nice things happen. And so general fact dealing with groups in characteristic P, if you have index multiplication stuff, that tells you that you can often reduce for local question. Okay, so now next definition. Okay, yeah, so this is saying any indecomposable can be associated with a subgroup. Now, and for instance, if M is a simple, right, then this subgroup you get is the no. So I was going to say it's the defect group. Is that true? No. It'll be it's related to the defect group of a block. Yeah, if you look at all of the things in a block and you take these things, the minimal one which works for all of them is the defect group of that block. So this is related to defects.
Smaller.
What's that?
The vertex will be smaller in general. The current.
So the vertex will be bigger.
Bigger, right?
Bigger.
But how would it be bigger? When M was projective, then wouldn't you get the identity subgroup?
Yeah.
So it would be small.
Oh, sorry, probably you're right.
Wait, so no, I think you need the minimal one which works for everything in there.
Well, that's for the defect group. I'm saying that if I have a general module, its vertex will be a subgroup of the defect group. That's what I'm trying to say. If it's if for the given block that it's lying in.
Oh yes,
Yeah.
yes,
That's what,
yes,
okay.
yeah.
That's right.
Yeah, okay, yeah. Right. Okay, so so now the new definition is a source of M. So U is in rep Q, okay, where Q is the vertex of M. If U is indecomposable and M is a summand of the induction. Okay. So now let me state the sort of trivial but very important lemma, which is that some source exists. Source for M exists. Okay, so let me prove this lemma. So okay, we know that M is relatively Q projective. So that tells us that M is a direct summand either of this thing or of the induction of IGU for some U of Q. But if you broke this up into indecomposables, it would have to be a summand. Well, because this preserves, summands, that means when you induce, the thing breaks up into summands, and this M being indecomposable tells you that it will live, that it'll be isomorphic to a summand of one of those pieces. Okay? So that says that, like, I've said it works for some U, but really, like, we can take U to be indecomposable because M is indecomposable. Because our categories are broken. Okay, and maybe I'll just.
Why didn't you Schmidt for that? I don't see.
I
mean, you just know that M is a direct summand of a sum of things, so it has to be a direct summand of one.
That requires Schmidt because
I don't think so.
Yeah, I mean, imagine if you don't have a uniqueness statement of how you decompose your summand. Like, for instance, take two line bundles on a space. There's some.
I just need that M is indecomposable and has endomorphisms local ring. Ah, okay. Yeah, I guess if I know the endomorphisms of M are local ring. Okay, never mind.
Oh, yeah, sorry.
That's only use M.
If you have a endomorphism restriction, possibly on just on M, maybe.
Yeah, sorry.
Yeah, but yeah, like we really use the uniqueness.
Yeah. Okay. Sorry.
Okay.
Will you explain the terminology right now? I'm confused why the source is in the vertex. It's a bit strange.
Yeah, so I think maybe someone else can say better, but like I think source makes a lot of sense. So maybe I should say is a source, but the theorem I'm about to say is that it turns out the source is independent, or like the isomorphism class of this is independent of things. So how I think about this is like G, some big thing, you've got your Silent P subgroup sitting inside it, you've got all of these little ones inside it. Then, yeah, vertex, I don't know, but it says any indecomposable M sort of corresponds to an indecomposable in one of these smaller pieces. And the source is like, once the vertex is where it comes from, which Q that it comes from. And the source is like what it comes from within its location. So I think the vertex points at the location of where to look. And then the source says, okay, well, now I'm looking in the right place. What is it? But yeah, maybe, just, no, you don't know the name. All right. Does anybody know the, yeah.
Yeah, it just looks very weird. The source is in the vertex, which is.
Maybe you could imagine like, the vertex is like the location of, I don't know, a spring, or like a location of a spring in a forest, and the source is the actual spring itself. And so this is telling you your general region, and this is saying, no, okay, it's behind this boulder or something.
Okay.
I don't know if that speaks to it, but like, I do like the word source. I think it's great. Vertex, I'm a little bit like, I don't know.
Right, source is fine, but vertex is some. I don't know.
Vertex is a little bit. All right, now, is everybody comfortable why some source actually exists? Because this is sort of trivial, but it's very important. Okay. So now I'm going to give the theorem. And I'm also going to give the proof of the theorem, and it's going to be reasonably involved. So I really want you to sort of interrupt me if you don't keep track of all the moving parts, because I think this is a really beautiful, like, general principle to try and be at peace with. So we've got lots of time, and this is sort of the only thing I want to talk about from now. So like, let's all really try and understand what's going on. Okay, so U a source. So again, M in rep G. Q its vertex. Okay. So then U a source of M is unique up to NGQ conjugation. Okay. And induction, maybe I'll say induction summand and restriction summand yield a bijection between the following two sets. So maybe to state it in full generality, say we've got some subgroup K that contains the normalized group Q, named in G. So we could take K to just be the normalized group Q if we want. Indecomposable K modules with vertex Q. And then indecomposable G modules with vertex Q. And, you know, I'm saying K and G, they're sort of sitting above the normalizer, but really both of these sets are in bijection with the indecomposable Q modules of vertex Q mod the normalizer conjugation action. Oh, so really I should be saying all of these up to isomorphism. Okay, so now I'll tell you what these ind and res are. Well, maybe even writing the functorials isn't the best, but yeah, so this is the theorem. It's sort of saying sources are unique, and you basically got a bijection. So just looking at this half, this says, okay, indecomposable G modules with a given vertex correspond to indecomposable Q modules with a given vertex. But then you got to mod out by this conjugation action of the normalizer. And then if you have this correspondence for some G, like if you can go from here to here, then you can also go from here to here. And so you can also go from here. And this correspondence is given by induce, take a summand, or restrict and take a summand.
Like a particular summand, you're saying.
Yeah. Like,
Just tell us how to find it.
well, it's sort of like there is a unique
unique
summand
yeah.
which works. But yeah, we really want to think of these not as like functorial operations, because we have to take summands inside stuff, and you can't do that functorially in this Cross-Schmidt world. But you do get isomorphism classes. So this should really be thought of as a bijection on isomorphism classes of objects. Okay, so does anybody have any questions about the statement of the theorem? Yep.
Do we need to mod out in the decomposable K modules?
No, because K contains the normalized group Q. Okay, so now, because I do want to go into the proof of this, but I'd also like to just say a few words that, like, this is an insane theorem. Like, you know, it's every indecomposable G module, you know, that's the whole category rep G. We want to understand the category. right? Representation theory, you want to understand. This is telling you precisely where every indecomposable G module comes from. So it's like a complete classification, except it's one of those complete classifications that shows you that your problem is basically intractable, right? Because these guys are, the representations of a P group in characteristic P, we already know that those are like Y. Those are really, there's something crazy. So this is telling you that you're gonna have heaps of indecomposable G modules, and there's nothing you can do about them. But I really wanted to stress that this is like an amazingly powerful classification theorem. Well, an amazingly powerful theorem which tells you the structure of this category. It says everything comes from Q subgroups and then normalizers.
Do I understand this correctly? It looks to me like, just to follow up on your comment, that I have finitely many indecomposables if and only if my P pseudo subgroup is cyclic, because for the cyclic group I have just finitely many indecomposables, and the theorem tells me that I can induce them up.
I think so. Yeah.
It's pretty cool.
Oh, and something which I actually didn't prepare, but does this work blockwise? There's a block. Is this true on the level of blocks once you define the corresponding blocks?
Yeah. But I'm not exactly sure how to formulate it.
Okay. So in the presence of the right formulation, this probably descends to a blockwise thing. But for now, we can leave it at this. And the idea, I think, is that if in general you're just dealing with additive structure, what you're doing probably works blockwise. For instance, you're looking at symbols, you're looking at projectives, kernels, co-kernels, like summands, that kind of thing. As long as you're not dealing with tensor products, then it's probably okay.
When you say blockwise, though, I mean,
What do I mean by that?
which blocks are you talking about downstairs? You starting with some block upstairs, and then which block?
Yeah, so this would be I think it would sort of be a weaker statement for an indecomposable module will sit inside a certain block. So that means this set globally has a block partition. And then I think my claim is that the Qs you get downstairs should also then have a global partition, right? Like the indecomposable Q modules of vertex Q will have a block decomposition just because these guys have a block decomposition.
Well, the indecomposable run. But there's only one block down there, right? Or you
Oh, as in take over all the Q subgroups at once. So like maybe a better way to say, because there is only one block here. But if you look at the set of all of these indecomposables, all isomorphs and classes, all indecomposables, that has an equivalence relation given by blocks.
Yeah.
And so that induces an equivalence relation on the set of all indecomposable Q modules with vertex Q
okay.
over all subgroups, over all the P subgroups sitting inside the group.
Okay.
And then I'm pretty sure there is an alternate description of that equivalence relation, but I don't have the precise name. I think that involves the Brouwer mechanism.
Okay.
Chris, I have a question.
Yep.
If you took Q to be the identity, wouldn't this be saying, or the trivial group, wouldn't this be saying there's only one indecomposable projective G module?
Oh yes, you're right. Yeah, you're right. Sorry, I made this mistake. I was thinking about it before. Yeah, so oh god, sorry. So yes, you're completely right in that there is a way to go from here to here. Yeah, so the statement is you have a map from indecomposable G modules to things here, and you have a map from indecomposable K modules to things here. And then they match up via induction, so you can match them up. However, things down here can be hit by multiple things. So, yeah, so you don't have a bijection here. Yeah, sorry, you don't have a bijection there. So maybe I'll draw sort of a toy picture of what's happening. Say we've got 4 elements up here, 2 elements down here. This is saying that we've got like, say, a surjection here and a surjection here. So like imagine we just got a set of 4 elements, set of 2 elements, and then got surjections here, surjections here. So this is the setup of the theorem, where these are things with vertex Q, and these are things with vertex Q. They're all mapping onto things down here. And then induction and restriction give you sort of ways of matching up the fibers of these two. That's that's how I would think of it. So like different indecomposables can have the same source. Yeah, different indecomposables can have the same source, but when you induce, it induces a bijection on the source, on the things with that source. Right, yeah, because if U is the source and we induce it up, this can have multiple indecomposable summands. So like it's not saying that there's a unique thing if you induce, it's saying there's a unique thing if you restrict.
I thought the problem was that you're inducing Q, not, I mean, they're the issue
Sorry.
that you're inducing Q.
Yes,
Opposed to
yes,
the
yeah.
normalizer, yeah. You're using the normalizer, then there'll be a unique summand with the right vertex, but if you just induce from Q, then there could be multiple summands with vertex.
Yeah. Oh yeah, right. So, but okay, then Alan's comment of what happens when Q is trivial tells you that you're going to have like one thing down here, lots of things up here, indecomposable projections.
Yeah.
And then, yeah, so you will be in the setup where you've got like large fibers mapping down. Oh, and then we can check when we induce the trivial thing, we get the regular representation. So that does break up into many indecomposable projectives. Yeah. Okay, yeah, sorry about that. I've made the exact same mistake twice. Once in private, once in public, but that's all right. So yeah, so the thing that gives you a bijection is induction and restriction on these overgroups. But this vertex source stuff is a very well-behaved surjection onto these things. And then induction and restriction are like ways of identifying the fibers of those surjections.
Is there any like nice situation when it is in it, those downward arrows are bijection?
And NG of Q is Q.
Which happens very rarely. I guess, yeah. Oh no, well.
That means it would have to be a CLOP already. Because its normalizer inside the CLOP will be bigger.
Yeah.
So maybe that happens, I have no idea.
Yeah, I mean, I feel like that probably, yeah. So that can happen. Take C2 inside S3. So like,
That's true.
yeah. So that can happen, but that's not the norm. Okay. So now I think hopefully all understand the statement. So let's see how to prove.
Maybe just a comment
Yeah.
that, so I think that the picture one should have in mind is you have this big group called G and this much smaller group called Q. And Q is, for example, a PC log subgroup. And so you have this big thing and then you have this small thing sitting inside it, but it's not really well defined. It's only well defined up to conjugates. So it's sitting inside it many times, lots of different copies. And there's also lots of different ways of going, like once we conjugate this thing around, we get lots of different copies of it. And generally in mathematics, when you have like a whole lot of objects that have a whole lot of maps between them, so that's that a whole lot of isomorphisms, that's called a groupoid. And a groupoid is always equivalent to just the thing together with the isomorphisms of it to itself. And so that is exactly what NG of Q is. So in some sense, you have this big group, you have this groupoid of all, let's say, the Syllopy subgroups, and then you can reduce this groupoid to the normalizer. So roughly speaking, that normalizer is saying, how does this little group kind of sit inside, what's the local information of how this little group sits inside this big thing? That's NG of Q.
Yeah, so maybe adding into that, like in general, like in a general setting, if you've got a group and its Syllopy subgroup is normal, so everything fixes it, you can understand it in a much better way. Like basically everything is better when more subgroups are normal, right? When all of your subgroups are normal, you're almost abelian. So like your life is better when more subgroups are normal. And this is like this local information. Importantly, the subgroup that you care about is actually normal. So for instance, just taking the like Q to be inside of the subgroup, this tells you that you can assume that it's normal in this situation downstairs, or in this situation, right? The normalizer of the thing. And that's like, for proving things, very helpful. Yeah, it's a lot easier to do stuff. Because for instance, that tells you that your quotient, at least if you take the Syllopy subgroup, the quotient will be co-prime to P, and so you would expect it to be really well behaved in characteristic P representations. So yeah, so this is like it's much nicer the closer you are to this. Like if you're in this setting, it's much easier to analyze things because then you don't have a bunch of conscious classes in the bracket. So now let's prove this. And the proof of this is just repeated applications of the Crull-Schmidt property, relative projectivity, and the Mackey formula. But there's a lot of moving parts. Okay, so observation 1. U, a source of M, then, okay, by definition, GU, this is definition. Then we also have U is a summand of the restriction for that. Okay. So how do we prove this? Proof. So U is a summand of restriction okay. And we also have okay, yeah. So we have that U sits inside here as a summand by the Mackey formula. And we have that M sits inside like U, G by definition. So that means sits inside as a summand. So the restriction sits inside. Okay, but now let's actually write out what the Mackey formula for this means. Okay. direct sum of QGQ. In here, induce up to Q intersect QT with a restriction of the adjoint like twist of U. Okay. So now when this double coset lives in the normalizer, this intersection will just be Q. And when this double coset does not live in the normalizer, this intersection will be strictly smaller. Okay, so we can rewrite this as T in the normalizer mod P of add T of U, direct sum, reduction Q, smaller stuff. And by smaller stuff, I mean it's induced from smaller subgroups.
Your cubic note P.
Sorry, yes, my cubic note P. Okay, so what do we have? We have that the restriction, this restriction is a summand of this, which means that some part, like, let's basically put this fact and this fact together. Okay, so RGQM breaks up into indecomposables. Which indecomposables could it be in this formula? Well, the claim is that it can't be contained in any of the in all of this, right? Because if this broke up into summands, those summands were contained in here. That would tell you that M is a summand of an induction of stuff which is smaller than Q. Okay.
But I guess like somehow you're talking about Q modules right now though, right? So you're kind of also claiming some sort of compatibility between this decomposition of Q modules and the fact that it's also a G module. And maybe it's not obvious to me, but do you understand what I'm asking? Like, I mean, it's not like that's a direct summand of G modules.
No, like all of this is taking place in Q.
Yeah. So yeah, maybe it's, I just don't fully see it.
So maybe let's go back to it. So what we want to show is that U sits inside of this thing. And what we want to consider is like U, sits inside here as a summand, and then this sits inside here as a summand. And we want to show that it sits inside here as a summand. Okay? How might we do that? Well, great. So the restriction of this sits inside here as a summand, and then the claim is that this part sits inside the restriction of Q to M. Okay, how do we see that? Well, this is a summand, which means it either contains, it contains some amount of this stuff, some amount of this stuff, up to isomorphism. If it contains any one of these, it also contains its translates because it's a restriction from G. Which means our options are, it contains some summand, hence all of them, or it's contained in here. But it can't be contained in here because it's like Q is minimal for which it's relatively Q projected. And that tells you that some summand here must live in the restriction, but because it's G G contains the normalizer, that means all of these things must live in the restriction, which means that U itself must live in the restriction. Yeah, so I will say that I find this stuff surprisingly difficult, given that none of the concepts are high concept. It's just summands, and it's just summands and functors, but I still find it quite difficult. So yeah, we can go over it more as well if we want.
You're using that composition and induction, like again, induction. If it sat in the second hand, the right hand side, then you'd find that the induction from Q up to G would contain n to some n. On the other hand, then you're inducing first from something smaller than Q, then up to Q. So it's really just something smaller up to G, and you find that m is direct sum n, but then that contradicts the fact that Q is over.
Yeah, cool. Okay. Fantastic.
And this ends up becoming an equivalent definition of source, yeah, is that?
Yes, so I'm proving uniqueness of source. And
So-
yes.
So like U is the source of M, the original definition is in the top right, but it is equivalent to U is actually a direct sum of the restriction.
And it's not, and that this is relatively, like, you can't express it as a something smaller
Mm.
use states.
Its vertex itself is Q.
Yes, that's what it is. All right. Now, okay, now we can show uniqueness, right? So say we have U prime, two hypothetical sources. Then from the previous, we have that U is a summand RGQ
Could you explain, sorry, once you have one of them, could you explain again how you get all of them?
Yeah, so the idea is this thing is the restriction of something from G. And if you have a summand, like if U is a summand, then thinking about all the summands that occur, that must be invariant under the NGQ action, because thinking of this has an action of the normalizer, this NGQ. Yep, if you pick an indecomposable thing in here, and you hit it with an element of NGQ, you get another indecomposable, which is this, once you restrict to Q. So this is like the Clifford theory all over again, but now it's not with simples. It's like the normalizer sort of commutes these things around, and if they're not isomorphic, then in fact they'll be disjoint, like the Clifford theory thing. Or yeah, I think so. And so then, because of that, if you've got one of them, you'll actually have its whole orbit. And then that tells you that you will in fact have the U that you started with. Any more questions about this one? So we can nearly prove the uniqueness, and once you prove the uniqueness, it's like it all sort of follows. Like this is the core part of the proof. So, and then we also have that M is a summand I U G U prime. All right, so this is by definition that it's a source. This was by what we just did. So that means we have RGQ is a summand of this. So putting these together, because direct sum is a transitive relation, I've been writing it. GQ G U prime. Now again, by the Mackey formula, this thing is the sum of GQ mod Q add T Q, right? Add T of U prime, direct sum induced from smaller. And this is indecomposable, so it lives somewhere here. And thus, it must live in this one because it's not induced from anything smaller, which tells you that there's some element here which conjugates between U and U prime. Okay, so this at least finishes the uniqueness part of the proof. And once we know the uniqueness, it's actually not so hard to show the other way around, right? So if you take something in here, take some M, you induce it. If, say, some M sits inside I, Q, K of U as a sum end, then when you induce it, it will also sit inside. Right? So if this is sitting in this situation, and then you induce, well, you get that I K G M sits inside I K U right, Q G U, which means that an indecomposable sum end of this will sit inside here, and then you just need to show like an indecomposable sum end which sits inside here. There will be a unique one with vertex Q, which I think then you can, or maybe it's easier to verify this using restriction. Yeah, but I guess my claim is that once you sort of know that everything inside is unique, then that tells you that you have surjective maps here, which are all defined by restriction compatibility. Oh yeah, okay. And so you have something here, so there's a unique thing with a vertex here when you restrict it, but that means you could restrict it to here, and there will be something with vertex Q here, otherwise you'd be relatively projective for a smaller subgroup. And you can't have multiple, because when you reduce it here, there's a unique. So yeah, it's like the fact that finding the source is given by restriction tells you that this like horizontal arrow will induce bijections on all the fibers. Would somebody have a question on this?
Maybe just a comment that it's just like, it's bonkers how it's actually like Mackey formula and Krull-Schmidt just give you this ridiculous amount of structure.
Yeah, and like, yeah, it's absolutely insane, like, because that's all you use. You don't use anything else. So you could imagine in any category with Krull-Schmidt type properties and objects with a G action, you could do this. So, and like, there are a hell of a lot of categories like that, more exotic than just representations. Like G equivariant objects in any Krull-Schmidt abelian category. Yeah, and this sort of works uniformly with the same group in all of those settings. So this is really just something fundamental about how sum ends interact with the Mackey formula, which is kind of yeah, it really sort of gets at the essence of things because it works in so many situations. Okay, great. Well, we'll maybe stop there.